I hope you all can see my screen okay there.
Oh, sorry,
Unmute.
Sorry, thought I had unmuted, but I guess I clicked it twice. Anyway, I had to come up with kind of an interesting title for what I wanted to talk about, and hopefully you'll get what the boom is towards the end of the talk. Okay, so I kind of think that Earth is the canonical habitable spectrum planet, since this session is supposed to be about habitable spectrum. I think since the Aegean, we all would agree there are long periods of habitability, and there were short periods where conditions were hostile to life, everything from snowball, slush ball, impactors, we'll talk about that a bit, volcanism, and of course what orbital dynamics does to the climate as well. And could some of these tipping points lead to long-term uninhabitability? I think those are things we should think more about. And I think we have to compare more to Earth through time rather than just modern Earth. So I'm glad to see that we saw that from Stephanie's talk earlier this morning and some other talks, because I think we have a tendency to look at either aquaplanets or modern Earth, and there's a diversity that we should explore because we have some data, even if it's not the greatest data, that I'll talk about in a few minutes. So this is not another impactor talk, contrary to the title you saw. I think that the normal humans, not most of the humans on this talk, think that impactors are kind of the final arbiter of habitability, as they say here, because we think that that's what's going to wipe us out in the short term if climate change doesn't get us first. But there are other factors to consider regarding this kind of long-term habitability. And I think part of the problem is that we have some problem with current thinking. There's contentious timelines in Earth history that are playing their part. And there was a very nice commentary by Planaski et al. In just the most recent issue of Nature. And you can see here that there's huge debate still going on to understand Earth's history. And all of the orange ones are things under debate. You can see here, when did oxygenic photosynthesis begin? When did life begin? The Snowball glaciation at 2.4 gigayears ago. What were the triggers for the various mass extinction events? A lot of this is sociological more than scientific reasons, is because people don't like to share their rocks, apparently. I recommend reading the article to see what's going on. So there's a lot of uncertainty just in the Earth record. I think this goes back to what Adrian was saying, it's hard to get people to agree upon things in general when it comes to understanding the Earth. And this is the planet we have the most data for and will always have the most data for. I would say science does play a part too. Again, hard snowball versus slush ball. Did we have hard snowball phases, or were they more slush ball type phases? And I think that there's debates about that at different stages of Earth's history. And then, of course, human bias playing its part, as I said, which may not be so useful when we're looking at long-term habitability and exoplanetary science. But I like this quote that's from a 2017 paper by Bond and Graspy, where they say, as you see here, despite much searching, there remains only one confirmed example of a bolide impact coinciding with an extinction event on Earth. And I think that, again, in the popular mind, that would be very surprising because it's so compelling. I love these pictures that they are showing always with, there's always a T-Rex in the picture, there's a giant fireball. After the fireball is hit, you still have a T-Rex, and occasionally humans show up. And this is one of my favorites. You get the occasional volcano, bang number one, and then this rock is coming in, bang number two, and here's a T-Rex just had his dinner with a triceratops. So I think they're really compelling, but I don't think that important in the end. And I think that one thing we've overlooked in our community a bit is large-scale volcanism, or what's termed large igneous provinces, and I'll explain why I'm so interested in that towards the end here. I think it's pretty clear that they're responsible for dramatic climate change. I'm not going to go into details about that, but I think that's true. I think that they're responsible for many of the mass extinction events. They were many of the orange dots we saw in that Planaski et al. Plot earlier. And I think you might even know some of the biggest, baddest ones, as they say, or the super bad ones, as James Brown would call them. We have the Siberian traps, which is believed to have triggered the end Permian. Of course, when you see the end of something, you know something bad has happened. You have the CAMP, the Central Atlantic Magmatic Province. That's the end Triassic, 200 million. There's a Deccan Traps. I think that's the most famous one that you might have heard of, which is related to the end Cretaceous about 65 million years ago and is related to the extinction of the non-avian dinosaurs. But occasionally people get it right. This is Ars Technica from 2017, who do point out that most mass extinction events began with these vast convulsions of Earth's interior, and they're asking whether we can detect that. And I would say that large-scale volcanism, as you can see here, is a constant throughout Earth's history and appear to be random events. And in a recent paper, we even asked, has Earth been a bit lucky? Imagine you have a couple of these go off at the same time. How is that going to drive climate change in a way? And you can see not only did they happen temporally at what looks to be fairly random times, but also spatially. And so here you can see some of the biggest eruptions. This is again a Nature piece from a few years ago showing where they tend to be all over the planet. Richard Ernst has been one of the big collectors of this data and has published a couple of nice pieces showing the dates of the events and their locations and their sizes. These large igneous provinces tend to be of order 10 to the 5th to 10 to the 6th square kilometers, and the same order of magnitude in terms of cubic kilometers and time as well, believe it or not. Okay, but there is at least one case where it can be both volcanism and bolide, and this is a beautiful plot just to show, for those of you that don't look at geology stuff so much in the literature, this is from Schoen et al. In 2019, Science, showing the Deccan Traps versus the Chicxulub impactor. So there's been fights in this community for years about, what was the final arbiter? Was it the bolide that came first and then the traps came after? Or was it the traps that came first and the bolides came and finished them off? You can read papers from 15, 20 years ago where people on each side take very strong opinions about this. But I think the evidence is that is more or less what you see here, because people have spent a huge amount of time looking very carefully at these large igneous provinces, in this case, the Deccan Traps. And I think this is just one of these really beautiful graphics. So you can see on the bottom is the topography of the Deccan region. In the A, you can see where the line is drawn, where they made all these different sample points. And then you can see on the x-axis here, time going backward from left to right. And you can see that the impactor sits right in the middle. So it's not clear, I guess in a sense, if one was unique in a sense, but clearly things were happening already on the planet, which were not good for life on the planet. And perhaps it really was the impactor that finished off the non-avian dinosaurs in a sense. So now what I really also want to focus on is whether Venus is perhaps the other canonical habitable spectrum planet. So this is related to a paper that Tony Del Genio and I published just recently in JGR Planets. And I'm not going to go into a lot of details because the talk would take at least an hour to go through, but I just want to cover a few highlights and talk about how I think these large igneous provinces and other internal events play their role, possibly have played their role in Venus's history. So first we have to assume that the magma ocean lifetimes of order a few million years. Tim talked about this a little bit yesterday. There's this classic Keiko Hamano work that has shown that Venus is right at the boundary of whether it will have a long-lived magma ocean, say of order 100 million years and started out bone dry, or whether it had a more Earth-like longevity magma ocean, which is just a few million years. We really need exoplanet observations to confirm where a planet like Venus sits in this sense. Our models are great, but models only take us so far. Another thing you need is this slowly rotating planetary cloud feedback. A high cloud fraction was proposed for Venus all the way back in 1971 by Jim Pollock. He didn't give any rationale for it. He did one 1D model with 100% cloud cover and one with 50%. And the 50%, the planet went runaway 4 gigayears ago. And then he did one 100% and it was about 300K. And it wasn't until 43 years later that Jun Yang and Professor Doriano's group at U Chicago showed from exoplanetary studies that slow rotating planets can give us this cloud feedback that was predicted by Jim Pollock back in 1971 that really keep the surface cool under actually ever increasing solar luminosity. Then the question is, did water ever condense on its surface? That's a question we do not know the answer to. And in the paper, we try to explain what evidence there is for that, but really we have to go back to the surface of Venus and do a lot more observation to constrain that. Then the question is, if the planet was habitable, how did it become uninhabitable? And I think it might have been via interior process. This is our other bang from simultaneous large igneous provinces, is what we propose. And then the question is, if this planet had large amounts of water on its surface, where is the oxygen? That has been discussed also in previous talks here. And that has been a sticking point for early habitability of Venus. If you have significant amounts of water, it's not too hard to lose the hydrogen, as we've seen in previous talks, but it is very difficult to get rid of the oxygen. And I think we have a potential solution for that as well. But I would just want to point out that typically these two canonical models of Venus were that it started out bone dry because this magma ocean lifetime was too long, and the other was that it had a short period of habitability, and that it was solar insolation through time that drove the planet into a runaway greenhouse state. And I think we already showed this in our kind of infamous 2016 paper, Was Venus the First Habitable Planet in the Solar System? That is probably not the case. If this cloud feedback mechanism we see in GCM models is correct, increasing solar luminosity through time plays very little role in increasing surface temperature on the planet because the cloud feedback effect is so effective. Okay, so this is basically my last slide, which I'll spend some time looking at. So this is an annotated version of one of the figures in our paper, which you can see on the right here. And this is what I would call a speculative Venusian climate history. And I should say from the start, almost everything here could be completely wrong, except for the very beginning where I say magma ocean period, and at the end I say resurfacing period. Everything else in between is up for grabs. But I'm just going to point out here a few points of interest for us, and I'll get to the volcanism towards the end a bit. Each data point you see here are a suite of 5 simulations that we've done with various amounts of water inventory on the surface. And what you're seeing in the data point is the mean temperature value for those 5 data points. So the first data point, because of course we assume that the planet did, of course, have liquid water on its surface. And in this cool early Venus phase, which goes back to a term used by Eric Chassaferi, when we still believed, I think, well, probably most of us still believe in the large late heavy bombardment, but there's increasing evidence that late heavy bombardment may not be as late as we thought it was. But we start out with CO2 dominated atmospheres, 1 bar CO2 dominated atmospheres. We believe that these first atmospheres, these first post-nebular atmospheres were probably CO2 dominated. And you can see here that the mean surface temperature is around 46, 47 degrees centigrade. So you can still have liquid water on the surface of the planet at that stage. We assume some sort of volatile cycling has taken place. And again, we think always in terms of comparative planetology with the Earth, in that it looks like Earth has had volatile cycling for most of its history. We can see that in the rock record for the Earth, whether it was subductive plate tectonics or, as Brad talked about yesterday, single plate volatile cycling of some sort. Whatever it was, we know we've had volatile cycling on the planet for a very long time. How it got started is, again, a hot topic of debate in the community. Then we move along to about 3 gigayears ago, and then we go to an N2 dominated atmosphere, again, assuming that it would follow a path similar to that of modern Earth. And we did a couple different, again, these 5 types of water inventory simulations with a 1 bar N2 dominated atmosphere, but we also did a 0.25 bar N2 dominated atmosphere. I'm just showing you the 1 bar one here. Again, we picked the 0.25 because we're interested in understanding whether or not this period in Earth's Archean history can also play a role, looking at thinner atmospheres and what kind of temperatures they have. And I can tell you, as you have already guessed, that the surface temperature would be lower in a 0.25 bar. Again, these come from Archean rocks that have been measured, and there's some debate about what they're telling us, but the lower end estimates are about 0.25 bar. You can see, again, on the y-axis, we're going forward in time with solar insolation increasing. Then we get to about 0.75 million years ago, or 715 million years ago. And again, here's these suite of simulations again. And you can see that even with the solar insolation increasing, we don't see a big increase in surface temperature for these 5 simulations. So I think what this is telling us is that, again, if water condenses out on the surface of this planet early on, it has a temperate climate, it will keep a temperate climate for this whole period of time. And so something else has got to happen that drives the planet into the state we see it today, if this picture it is all correct. And that's what this gray bar is that you see here, this large igneous province period, or something like that, where basically on Earth, most of our CO2, as you know, is locked up in rocks in the crust, whereas in Venus, most of its CO2 is probably locked, its superficial CO2 is sitting in the atmosphere. And the idea is that these large volcanic events would be the trigger to release most of the CO2 locked up in the planet. Your plate tectonics shuts down, be that as it may. Your volatile cycling shuts down. And over a few 100 million years, you start moving into this runaway greenhouse state. So your oceans evaporate, your hydrogen escapes through time, and then you're left with this planet with huge amounts of oxygen. And the question is, what do you do with all of this oxygen that's sitting around on the planet? So people have looked at this carefully, quite a bit carefully, and it has been clear from studies that the current surface of Venus is not very good at absorbing much in the way of oxygen. But the thing is that the planet's surface is, there are different estimates. It ranges between Botke's estimate of around 200 million to McKinnon's estimate of around 750 million for the age of the surface through crater counts. So 80% of the surface of Venus has been resurfaced with these large basaltic flats. Now these are separate from the large igneous province period. Again, these large igneous provinces would be things like the Siberian traps or the camp type traps that would be very large scale and again release the CO2 into the atmosphere while the planet still has plate tectonics going in the beginning, and then that eventually shuts the plate tectonics down because you lose your water, and water, as we know, is, or as we believe anyway, is crucial to modern day plate tectonics. This resurfacing period is something different. It's a different kind of process in the planet that is related to the interior processes, that some of which that Adrian talked about yesterday. So as you're resurfacing the planet, you're exposing huge amounts of fresh lava to the surface of this planet in this resurfacing period, and that would be very effective at absorbing the oxygen on the surface. So it's not the present day surface that would be absorbing the oxygen, which is cooled and cannot absorb more than a few centimeters deep worth of oxygen, which would not be very effective. But it would be the process over hundreds of millions of years that would be able to draw the oxygen out of the atmosphere. And as I said, you're left with this large CO2 inventory sitting in the atmosphere as we see today. I think this has interesting implications for us as a community, because there have been papers, as you know, by Lugar and Barnes, and Robin Wordsworth has also talked on this in the past, that we might find exoplanetary atmospheres that have lost oceans and would be full of oxygen, maybe thousands of bar type of oxygen atmospheres. And that may not be right if these interior processes that we're proposing are correct. And I haven't done the calculations yet, but I'm hoping this will drive some research into this topic. That might not be correct, and it might be that it turns out that these kinds of interior processes are very effective at drawing oxygen out of the atmosphere, and we're not going to find these, or we might find them in some cases, depending on what the geochemistry of the planet is and what's going on in the interiors of the planet. But it might be that they are not O2 dominated type planets, or not as many as we might imagine, that at the end stage of their evolutionary period. So again, this goes back to what we're saying before, that, you know, we have some idea that solar insolation increasing through time can drive you into a runaway. We know that Earth is at the sort of the inner edge of the habitable zone, and into the future, the sun's brightness will be such that it will drive the planet into a moist greenhouse and eventually into a runaway greenhouse state. But it might be in a lot of cases, it's not the solar insolation that drove the planet, and that it would be an interior process that drives the planet through things that we have actually seen in Earth history, and that we are fortunate enough to have seen larger versions of, or multiple versions of, at the same time. So I think we have to think a little bit more carefully about what we expect to see, in a sense. And I love this picture that Adrian showed in his Nexus talk a couple of weeks ago, where he showed a picture of Venus and Earth in their canonical places, and then he flipped them and said, what if we find this? We find an Earth-like planet at Venus's orbit and a Venus-like planet at Earth's orbit. We might find a lot of Venus-like planets at Earth's orbit, and that's something we should be prepared for going forward. So I think we should just temper our enthusiasm a bit, because I think that in general, we often, in our modeling efforts, in a way, we tend to find what we're searching for. And I think that applies to a lot of things. If you look at different types of time series analysis, if you look at, for example, these large igneous provinces through time on Earth, people have tried to relate them to periodicities that they can find in other ways. For example, boloid impacts, or where we are in our galaxy and things like that. And I can guarantee in almost any case, you can always find a reason for a pattern that you're looking for. I think the harder problem is to find a reason against the pattern. And maybe that's why we tend to do that. So I think we should consider, again, looking at Earth's history more carefully and seeing these kinds of things that we see have affected Earth in very bad ways, and how those could really affect other worlds in very bad ways, and may have actually affected Venus in its history. So with that, I'm going to end a bit early, and I'll take any questions that you all have. And hopefully I didn't overload you too much there.
Thank you, Michael.
Sure.
Question time, Norm?
Okay.